Lesson: Adversarial Machine Learning. Adversarial machine learning represents a critical intersection of artificial intelligence and cybersecurity, focusing on the vulnerabilities and robustness of machine learning algorithms when faced with adversarial attacks. As machine learning models become integral to numerous applications, including cybersecurity, understanding their potential weaknesses and developing strategies to mitigate risks become paramount. AML involves the study of how adversaries can manipulate input data to deceive machine learning models, leading to incorrect predictions or classifications. This manipulation can have severe implications, particularly in cybersecurity, where accurate threat detection and response are essential. One of the foundational studies in adversarial machine learning was conducted by Segedi et al. Who demonstrated that small, imperceptible perturbations to input data could cause machine learning models to make incorrect predictions with high confidence. This discovery highlighted the fragility of these models to adversarial examples and spurred a significant amount of research into understanding and mitigating such vulnerabilities. The adversarial attacks can be broadly classified into two categories: evasion attacks and poisoning attacks. Evasion attacks involve crafting adversarial examples that can bypass a trained model during its operational phase, while poisoning attacks aim to corrupt the training data, thereby compromising the model's integrity from the outset. Evasion attacks are particularly concerning in cybersecurity contexts, such as malware detection, spam filtering, and intrusion detection systems. For example, an attacker could subtly modify the features of malicious software to evade detection by a machine learning-based malware classifier. In a study by Gross et al., it was shown that adversarial examples could be generated to fool deep learning-based malware classifiers, significantly reducing their detection accuracy. This demonstrates the potential for adversaries to undermine cybersecurity systems by exploiting the vulnerabilities of machine learning models. Poisoning attacks, on the other hand, target the training phase of machine learning models. By injecting malicious samples into the training data, adversaries can skew the model's learning process, leading to degraded performance or biased predictions. A notable example is the work by Steinhardt, Ko, and Liang, who illustrated how poisoning attacks could be used to manipulate the outcomes of support vector machines and neural networks. In the context of cybersecurity, poisoning attacks could be used to introduce false positives or negatives in threat detection systems, thereby compromising their reliability and effectiveness. Defending against adversarial attacks in machine learning is a complex and ongoing challenge. One of the primary defense mechanisms is adversarial training, where the model is trained on a mixture of clean and adversarial examples. This approach, proposed by Goodfellow et al., has shown promise in improving the robustness of machine learning models against adversarial attacks. However, adversarial training is computationally expensive and may not generalize well to unseen attacks. Another defense strategy involves the use of robust optimization techniques to enhance the model's resilience to adversarial perturbations. For instance, Madry et al. Proposed a robust optimization framework that formulates the training process as a min-max problem, aiming to minimize the worst-case loss under adversarial perturbations. This method has been shown to improve the robustness of deep neural networks, but it also increases the computational burden during training. Detecting adversarial attacks is another crucial aspect of AML. Several techniques have been proposed to identify adversarial examples, including statistical tests, feature squeezing, and ensemble methods. For example, Feynman et al. Introduced a method that combines kernel density estimation and Bayesian uncertainty to detect adversarial examples with high accuracy. Similarly, Xu, Evans, and Key proposed feature squeezing, a technique that reduces the search space available to adversaries by applying simple preprocessing transformations to input data. These detection methods can serve as an additional layer of defense, complementing adversarial training and robust optimization techniques. In addition to these defense mechanisms, ongoing research in AML focuses on understanding the theoretical underpinnings of adversarial attacks and defenses. Theoretical frameworks, such as the adversarial risk analysis proposed by Bertsimus, Delarue, and Mishich provide insights into the trade-offs between model accuracy and robustness. RA involves the use of game-theoretic approaches to model the interactions between adversaries and defenders, enabling a more comprehensive analysis of adversarial scenarios. By leveraging these theoretical insights, researchers can develop more effective and principled defense strategies to enhance the resilience of machine learning models. The implications of adversarial machine learning extend beyond cybersecurity. In autonomous driving, for instance, adversarial attacks on image recognition systems could lead to catastrophic failures, such as misinterpreting traffic signs or obstacles. Similarly, in healthcare, adversarial examples could compromise the accuracy of diagnostic models, potentially leading to incorrect treatment decisions. These examples underscore the broader impact of AML and the importance of developing robust and reliable machine learning models across various domains. Despite the significant progress in understanding and mitigating adversarial attacks, several challenges remain. One of the primary challenges is the adaptive nature of adversaries, who continuously evolve their attack strategies to circumvent existing defenses. This necessitates ongoing research and development to stay ahead of adversaries and ensure the robustness and security of machine learning models. Additionally, there is a need for standardized benchmarks and evaluation metrics to assess the effectiveness of defense mechanisms. Current evaluation practices vary widely, making it difficult to compare different approaches and identify the most effective solutions. In conclusion, adversarial machine learning represents a critical area of research at the intersection of artificial intelligence and cybersecurity. The vulnerabilities of machine learning models to adversarial attacks pose significant risks, particularly in cybersecurity applications where accurate threat detection and response are crucial. Evasion and poisoning attacks can undermine the integrity and reliability of machine learning-based systems, necessitating the development of robust defense mechanisms. Adversarial training, robust optimization, and detection techniques offer promising avenues for enhancing the resilience of machine learning models. However, the adaptive nature of adversaries and the need for standardized evaluation practices present ongoing challenges. By advancing our understanding of adversarial attacks and defenses, we can develop more secure and reliable machine learning models, ultimately enhancing the overall security of AI-driven systems.